Hi friends, I am Rajesh. Welcome to my channel, Rajesh's Max Class. Today, I am going to take a result. R is uncountable. R means the set of all real numbers. So today, we will prove the set of all real numbers is uncountable. R is uncountable. R is uncountable. Clear? First of all, what is a countable set? Before that, we have to discuss the concept countably infinite or denumerable. Countably infinite or denumerable. Countably infinite or denumerable. Let S be a subset of R. S be a subset of R. S is said to be countably infinite or denumerable. Countably infinite. Countably infinite. Countably infinite or denumerable. Denumerable. S is said to be countably infinite or denumerable if there exists a bijection from N onto S. If there exists a bijection from N onto S. That means we can see a bijective map from N onto S. Suppose this is N. This is N. And this is S. S be a subset of R. If there exists a bijective map from N onto S, N onto S, then we can say that S is denumerable or countably infinite. Bijective map. Suppose 1, 2, 3, etc. And 1 maps to the first element in S1. That means we denote it by smallest one. Next 1 maps to, 2 maps to, smallest 2, 3 maps to S3, etc. Clear? That means if there exists any bijective map from N onto S, then we can say that S is countably infinite or denumerable. That means we can enumerate every element in capital S. This is the first element, and this is the second element, and this is the third element, etc. So S is called denumerable set or countably infinite. Countably infinite. Next, a set is said to be countable. A set is said to be countable if it is either countably infinite or finite. That means either denumerable or finite. That means every finite set is countable. Every finite set is countable. Every countably infinite set is also countable. That means every denumerable set is also countable. Clear? Next, a set is said to be uncountable. A set is said to be uncountable if it is not countable. If it is not countable. Here we want to prove R is uncountable. That means R is not countable. Clear? So we prove R is uncountable. R is uncountable. Clear? Here we use a result. Let A comma B are any two sets. A comma B are any two sets with A subset B. With A subset B. Then if B is countable, then A is countable. If B is countable, implies A is countable. A is countable. Clear? We use this result. A comma B are any two sets with A subset B. Then if B is countable, then A is countable. That means every subset of a countable set is countable. Every subset of a countable set is countable. Clear? If R is countable, then by this result, we can say that every subset of R is countable. If R is countable, then every subset of R is countable. Clear? What is its contrapositive? Contrapositive means if we consider the result P implies Q. P implies Q. Or if P is true, implies Q is true. Or simply P implies Q. The contrapositive of this result is not Q implies, not Q implies, not Q implies, not P. Or negation of Q implies negation of P. Clear? Contrapositive of this result P implies Q is not to Q implies not to P. Clear? For example, we have every convergent sequence is bounded. Every convergent sequence is bounded. A sequence is convergent implies a sequence is bounded. The contrapositive of this result is X is not bounded implies X is not convergent. Clear? X is sequence Xn is convergent implies sequence Xn is bounded. Sequence Xn is bounded. Sequence Xn is bounded. Contrapositive of this statement. Contrapositive of this statement. Here P is sequence Xn is convergent and Q is sequence Xn is bounded. So contrapositive of this result not to Q. That means sequence Xn is not bounded. Not bounded. Simply we can write BDD dot. Not bounded implies sequence Xn is not convergent. Clear? Convergent, CGT. Is a short form of convergence. So this is the example for contrapositive. Clear? That means contrapositive means if P implies Q, then it's contrapositive. Not to Q implies not P. Negation of Q implies negation of P. Clear? So here we have if R is countable. If R is countable, then every subset of R is countable. Every subset of R is countable. What is its contrapositive? Contrapositive is if any subset of R is uncountable, then R is uncountable. Clear? Any subset of R is not countable, then R is not countable. That is the contrapositive. Clear? Already we have if R is countable, then every subset of R is countable. Its contrapositive statement is if any subset of R is not countable, that means uncountable, then R is not countable. R is uncountable. Clear? So here we take closed interval 0, 1. Closed interval 0, 1 is a subset of R. Closed interval 0, 1 is a subset of R. If we prove closed interval 0, 1 is not countable, then by contrapositive method we can say that R is not countable. That means R is uncountable. Clear? If we prove closed interval 0, 1 is uncountable, then R is uncountable. Actually we want to prove R is uncountable. So we need only to prove closed interval 0, 1 is uncountable. Closed interval 0, 1 is uncountable. Closed interval 0, 1 is uncountable. So we prove closed interval 0, 1 is uncountable. In this proof we use contradiction method. That means we assume closed interval 0, 1 is countable. Then at last we will get a contradiction. So we assume closed interval 0, 1 is countable. Closed interval 0, 1 is countable. Closed interval 0, 1 is countable. First we denote this interval by capital I. So capital I equals closed interval 0, 1. That means I is countable. We assume I is countable. By the definition, we have a set is said to be countable if it is either a finite set or a countably infinite set. That means a denumerable. So here we assume I is countable. Then by the definition, we have I is either a finite set or a countably infinite set. But we know I is not a finite set. So I is a countably infinite set. I is a countably infinite. I equals closed interval 0, 1 is countably infinite. Countably infinite. Countably infinite. Countably infinite. So we can write every element in I in this way. That means I equals x1, x2, x3, etc. That means x1 is the first element, x2 is the second element, x3 is the third element, etc. That means we can enumerate every element in capital I. We can enumerate capital I. That means we can write every element in I in this way. That means x1 is the first element, x2 is the second element, x3 is the third element, etc. That means we can enumerate every element in capital I. Clear? Next we take a closed subinterval I1 of I. Closed subinterval I1 of I such that x1 does not belong to I1. I1 is a closed subinterval of I such that x1 does not belong to I1. Clear? First we take a closed subinterval I1 of I such that x1 does not belong to I1. Clear? Here we can write I superset I1. Next we take a closed subinterval I2 of I1 such that x2 does not belong to I2. Next we take closed subinterval I2 of I1 such that x2 does not belong to I2. Here I2 is a subset of I1. Clear? Also x2 does not belong to I2. That means x1, x2 do not belong to I2. Clear? Next we take a closed subinterval I3 of I2 such that x3 does not belong to I3. So we can say that x1, x2, x3 do not belong to I3. So here we can write I2 superset I3. Also we can write x3 does not belong to I3. Continue this process. Then generally we can write xn does not belong to In. Also I superset I1 superset I2 superset I3, etc. superset In, etc. Clear? Okay. Here we get nested sequence of intervals. Here collection I, set I, such that n belongs to capital N, is a sequence of nested intervals. Here we can apply the nested intervals property. Link of this theorem, link of nested interval property is there in my description box. Nested intervals property. We apply the nested intervals property. By this property, we have there exists a real number psi belongs to In for all n belongs to n, capital N. By the nested intervals property, we have there exists a real number psi belongs to In for all n belongs to capital N. Clear? So we can say that psi not equals x1. What is the reason? Here psi is an element in I1. If we put n equals 1, then this becomes psi belongs to I1. Psi is an element in I1. But here, if we put n equals 1, we get x1 does not belong to I1. That means x1 is not an element in I1. Psi is an element in I1. x1 is not an element in I1. So easily we can say that psi not equals x1. Similarly, we can say that psi not equals x2. What is the reason? Here we put n equals 2, then this becomes psi belongs to I2. That means psi is an element in I2. Also, if we put n equals 2 in this result, then we have x2 does not belong to I2. That means x2 is not an element in I2. But psi is an element in I2. So easily we can say that psi not equals x2. In general, we can write psi not equals xn for all n belongs to capital N. Psi not equals xn for all n belongs to capital N. That means psi not equals x1, psi not equals x2, psi not equals x3, etc. But psi belongs to In. Psi belongs to In. Also we have I superset I1, superset I2, superset I3, etc. Superset In, etc. Psi belongs to In for all In belongs to N. Then easily we can write psi belongs to I. Psi belongs to I. Because every interval is a subset of capital I. So psi belongs to capital I. Psi belongs to capital I. This leads a contradiction. Because firstly we write every element in I in this form. That means we write x1, x2, x3, etc. That means we enumerate every element in I. But at last we get an element psi in I such that psi not equals xn for all n belongs to capital N. All n belongs to capital N. So this leads a contradiction. So we can say that I is not countable. I means closed interval 0, 1 is not countable. So I is uncountable. Then already we have, if any subset of R is uncountable, then R is uncountable. So here we proved closed interval 0, 1. It is a subset of R. Closed interval 0, 1 is uncountable. Then easily we can say that R is uncountable. Clear? Okay. So I hope you have enjoyed my class. Thank you.